Hello, everyone. Welcome to the 105th online Spintronics seminar. Today, we have Dr. Geoffrey Diederich as our speaker. Geoffrey received a bachelor's in physics and with minors in chemistry and mathematics from Bowling Green State University in Bowling Green, Ohio in 2009, and returned to BGSU for a master's degree in physics, where their research focused on the synthesis and applications of colloidal quantum dot heterostructures. They received their PhD from the University of Denver, where they worked with Dr. Mark Simmons and received a Dean's Graduate Dissertation Fellowship in 2019. In their PhD, Geoffrey built a multidimensional coherent spectroscopy experiment and published a few papers on improvements to the MDCS technique while studying exciton dynamics in perovskite thin films. After their PhD, Geoffrey came to the University of Washington to work with Xiaodong Xu to perform ultrafast spectroscopic measurements on 2D materials, where they were awarded the ORISE Intelligence Community Postdoctoral Research Fellowship. Their current work focuses on the generation, measurement, and control of Exciton-Magnon, Magnon-Magnon, and photon-Magnon coupling in the van der Waals antiferromagnetic semiconductor, chromium sulfate bromine. And today we will hear some of his recent exciting results. Dr. Diederich, you have the floor.
Great, thanks, Shin. As Shin mentioned, my name is Jeff. I'm at the University of Washington with Xiaodong Xu, and I'm going to talk to everybody today about some recent work we've been doing over the last year or so to try and measure and control sort of the coupling of excitons and magnons, as well as magnons and magnons in chromium sulfur bromide, or CrSBr, as we sort of colloquially call it. The biologists sort of love that one. But yeah, so the title of my talk is Tunable Exciton-Hybridized Magnon Interactions in a Layered Semiconductor. And before we actually get started, I do want to just acknowledge everybody who did the work. This was clearly not all my effort. A lot of the exciton-magnon coupling results come from Dr. Yunju Bei in Xiaodong Xu's group at Columbia. This was recently published, and I will provide links and things a little bit later if anybody is interested. Crystals were grown by Daniel Chica and the group of Xavier Roy, also at Columbia. We received theoretical support from Yafi Ren, who works under Di Xiao, and Ting Chao also helped build up some of the models. And then in our own group, John Senker is a graduate student who really helped a lot with this, doing sample fabrication. He developed a lot of the strain apparatus that I'm going to show you later, and helped with some of the linear spectroscopy measurements. Jordan Fonseca helped keep all of our cryostats happy and running for these measurements. And then obviously my advisor, Xiaodong Xu, conceived the project and really helped with a lot of advice on the direction. Okay, so given the audience, I probably don't need to spend a ton of time on Magnonics, but really I'd like to sort of frame it in the way that is relevant to the work that I'm gonna present. And I'll just very briefly mention what a magnon is in case anybody is watching who doesn't really think about this sort of quantized version of spin. Yeah, a magnon we can think of as sort of the spin corollary to a phonon or something like that, right? It's a quantized spin wave. I sort of have a GIF right here showing what that looks like. We can disturb this sort of spin lattice that we have set up, and a few things will happen. One, our system will try and return back to equilibrium, or if there's a magnetic field applied, it will return to some direction that is defined by some effective direction that is defined by the applied field and the equilibrium orientation. And as it does that, it will sort of spiral in on itself, right? This is consistent with like the Landau-Lifshitz-Gilbert equations. The other thing that will happen is that it will apply a torque to neighboring spins, right? So this if I pick one, this spin right here, as it is disturbed away from equilibrium, will pull on nearest neighbors and next nearest neighbors. And this is how we get this sort of propagating spin wave. So the way that we typically generate and measure these things in experiments is we take some magnetic crystal. Here, this is labeled as Yig, yttrium iron, and garnet. And we'll pattern some contacts onto it, and we'll use one contact for generating magnons and one for reading magnons, right? And so we'll apply some AC current to this contact. If we sweep through a bunch of different frequencies of that AC current, each one of those will generate an AC magnetic field. And when we're resonant with the magnon mode, we'll transfer some of that energy into the magnon mode, which will then propagate. It will be collected by this contact, which is then sent to some lock-in detector or spectrum analyzer or something like that. And so we can measure the magnons that way. So this is great, but it's a little complex, right? It requires pretty precise device fabrication, and there's a lot of steps involved in that. So we'd love to see if we can get around that, which is something we'll get to. But why are we interested in these things sort of from a baseline level? I think a lot of the excitement recently from Magnons has really been for sort of quantum information or some information processing or transfer from that sort of standpoint. So most of this is really thinking about quantum transduction, which is sort of transferring energy from one sort of node or carrier to another. And for Magnons, these are really interesting because magnetic properties are typically very strongly linked to other properties in the system, right? So we can think about magnetostriction linking us to mechanical modes in the system, right? We know that there are certain opto-magnetic couplings, so we can link to some optical mode somehow. We can link between just the magnetic system itself and a magnon, and then the frequencies of these things tend to be convenient for things like superconducting qubits, right? They tend to be in the same order of magnitude, and so we can couple the radiation of these magnons to something like a superconducting qubit. And so these really hold a lot of power for what we call these hybrid quantum information systems, where we sort of transfer from one modality to another in a chain that allows us to leverage different properties. So that's sort of the transduction idea, right? We can also think about magnon information itself, right? And there's a lot of attractive properties of magnons for a sort of information processing or transfer scheme. One is that we don't need to pass any current, and so we don't need to have contacts on our devices. So other than this scheme right here for generating and detecting the magnons themselves don't need any contacts. And so if we could get rid of these, then we could have a very vastly simplified architecture for our devices. Magnons have been shown to be able to do wave-based computation, things like that, where we can do sort of larger scale simulations. And then again, because we're not passing any current, we have heat-free conduction, right? There's no Joule heating in the system, which makes them much lower energy. So our system is going to be AFM, and so AFM magnons are typically attractive because their lack of a net magnetization makes them more or less insensitive to external fields, at least less sensitive than an FM magnon would be. And based on the weaker coupling of AFM modes, they have a much larger range of frequencies that you can find or engineer them in. Somewhere from gigahertz to terahertz is possible or has been found in AFM magnons. So these are really a lot of attractive properties of these things for these information schemes. But again, what I want to return to is this idea of how we're currently generating and measuring magnons. And can we bypass this? Can we do this optically, for example, to have no electrical system necessary? It turns out, yes, people have done it, but the current ways of doing it are also quite complex, right? So you'll see here we have a sort of schematic of what this looks like in the current incarnation. And what we have is a ferromagnetic crystal with some magnon mode, and we can very precisely modify and then place an optical fiber such that it transfers or can transfer some of that angular momentum of the light to and from the magnon system. And so what you would do is you would pass in some polarization of light. You would measure at the end, and if there's some rotation in that polarization, then you can transfer or measure some of that information transfer that way. This is no less complicated than the system I've laid out here. And so the question I want to pose, which you can probably guess the answer to given the setup, is can we bypass all of this and just directly optically access the magnons in a system? So let's hold on to that as like the main question, and then just briefly talk about these layered 2D magnets for a second here. These have been pretty exciting and a huge topic in condensed matter research for the last few years since they were discovered in 2017. Actually, this discovery was a former graduate student in our group, Bevan Huang, who's now at MIT doing some cool stuff with graphene, where he showed that this crystal chromium triiodide does maintain ferromagnetism down to a single layer, right? Which was, I think, until very recently before that, theoretically not thought to be possible. And so if we look at these RMCD results from his paper, what we see is that in a monolayer, you have this ferromagnetic loop. If we switch to a bilayer, you have no net magnetization at zero field, and then you have some jumps where we have sort of spin flips. And if we go to a trilayer, you again have a ferromagnetic loop. So what this is saying at the end of the day is that these stack in what we call an A-type AFM order. So if we think about the layering of this van der Waals crystal, we have a monolayer and it's ferromagnetic. We put a second layer on, which is also ferromagnetic, but it couples antiferromagnetically to the first layer. And then as we stack layers, each individual layer is ferromagnetically coupled, but stacks antiferromagnetically. And so, I sort of look at this cartoon here where we show how we can stack these crystals. This would be like a spin up, spin down, spin up, spin down, so on and so forth. This turns out to be a really interesting property that a lot of these van der Waals magnets have, because we can exfoliate them to essentially arbitrary layer numbers and have some control over the magnetic ground state. So, the other thing that's interesting about these systems is sort of the variety of magnetic ground states we can have. This is just a quick sampling of what's been found so far in a lot of these layered crystals. And then finally, there's sort of the whole reason people are into van der Waals crystals in the first place is that their weak interlayer coupling means you can stack them, you can twist them, you can do all sorts of manipulations to the physical structure to make changes to things like the electronic, magnetic structure, et cetera. And so having magnetism now wrapped into that becomes a really interesting additional, it opens the parameter space significantly. Okay, so with that, I want to introduce the material. Again, it's chromium sulfur bromide. We call it CrSBr. And the lattice looks something like this. It's a rectangular lattice where the sort of spins that are active sit on the chromium sites. They are in plane along the B axis of the crystal. And they again have this A-type antiferromagnetic stacking, meaning, that each individual layer is ferromagnetic, as you can see in the cartoon, but they stack antiferromagnetically. Again, the only difference between this and CRI3 being that they're in plane now. I think a more interesting difference here is that CrSBr is also a semiconductor with a very strong excitonic response. So you can see the band structure right here. These black and red lines are just spin up and spin down bands, I believe. But you can see at the gamma point, there is a direct band gap, right? And so we'll have an exciton resonance there as well. The optical properties actually turn out to be really, really interesting in this crystal. And sorry, I actually forgot to mention, this is what it looks like when it's exfoliated. It exfoliates into these long rectangles. And we can get large, on the order of tens of microns scale, monolayers, bilayers. It's pretty straightforward. And all of this comes from a paper from last year from our group in Nature Materials. Yeah, so if we look at the optical properties, there's some pretty interesting stuff that starts to show up here. So this red curve is PL, this blue curve is differential reflectivity, and the dashed and solid lines represent excitation light polarization along the A and B axes of the crystal. And so what you'll see is that the optical response of this system is essentially unity polarized. There is no optical response along the A axis of the crystal. It is completely along B. And this actually leads to some really interesting consequences. There's a paper recently shown that even in bulk CRISPR, you can treat the excitons as one-dimensional. And so you have similar binding energies and excitonic properties to something like a carbon nanotube, but in a bulk crystal. So there's a lot of interesting stuff going on there. What you can see here is sort of the whole spread of that differential reflectivity data, across the entire range of polarizations. You can see at 0, 180, 360 is the only place you really get a strong optical response from the exciton, or this is the band edge luminescence here. And then finally, the temperature dependence of the PL looks something like this. You typically have a single PL peak. It narrows significantly as you lower in temperature. We have found that occasionally there will be a few more excitonic peaks. They're usually well separated, but sometimes you'll see 1 exciton, sometimes you'll see 4. We're not sure what the difference is just yet. I think it's a thing that's sort of hanging in the literature, and it will happen in the same crystal source, for example. So it might be something linked to the exfoliation process. Okay. So, so the optical properties are pretty interesting, but where this material gets much more interesting is when we start mixing the optical properties with the magnetic properties. And so what I'm going to show you is some magneto-PL measurements. So this is just photoluminescence taken while applying a magnetic field along different crystal axes. And we're going to start with this panel right here. This is a monolayer of CRISPR. You can see that the PL is about 1.3 eV. And as we apply field, nothing happens. We know that we're crossing, in the AFM state, what would be the saturating field, and we see no change. So that is sort of our baseline. But if we go to a bilayer now, where at 0 field we have an AFM state, you can see that, well, you can see two things, right? You can see first that our exciton PL energy has shifted by about 20 MeV, and that as we apply field, once we cross the saturating field, which has been measured elsewhere in the literature, that it shifts back to its original value, or shifts back to the monolayer value is what I'll say. So this is along B, which is the easy axis of the crystal. A is the intermediate axis and C is the hard axis. And we can see on those two axes, what we get instead is, again, we have this sort of 1.34 EV exciton at 0 field. It shifts down by about 20 EV once we get past the saturating field along each axis. But in between, there's a gradual shifting between those two values. And we know that this corresponds to the values that would give you a canting field, for example, again, because this has been measured in the literature. And so we want to know or we wanted to know what's going on here. And so Ting Chao at UW did some DFT calculations. Showing the difference between, this is sort of the band structure in the AFM state versus the FM state. And really the takeaway message here is that what ends up happening is that due to optical selection rules in the AFM state, the exciton is localized to single layers. So this gives you additional spatial confinement and increases that exciton energy. However, when you go to the FM state, your exciton is allowed to delocalize across many layers. And so that sort of confinement energy is lowered, your exciton and hole can spread out more, and so you see a red shift in the exciton. But interestingly, this is not a binary process. What the DFT calculation showed is that the degree of delocalization, and thus the energy shift, is proportional to the sign of the angle between spins in adjacent layers. And so if we think of a macro spin picture here, where we take each layer and sort of lump it as one spin, this AFM order has a large band gap. This sort of canted AFM order has a smaller band gap. And then if we go to FM, it becomes smaller still. And so we can use magnetic field to tune that exciton energy over roughly 20 MeV range. And you can see here, this is theory and experiment, and while the line shapes don't match, the shifts line up quite well. This is again from that Nature Materials paper from last year. Okay, so this is sort of this idea of magneto-excitons in this system. So if we do one more piece of background work, This is from earlier this year, a paper in Nature Nano from John Senker, who worked on the project I'm going to present with me. So what he tried then doing is applying strain to the crystal along the A-axis. So this is sort of a cartoon of what the strain apparatus looks like. It's a mount with 3 piezo actuators that pull in different directions, and then your sample is sort of suspended over a cavity, and then you can use those piezos to apply strain, again, here along the A-axis. And so what we see is at 0 strain, this is again Magneto-PL, and this is where we're starting to see these multiple excitons show up, but we don't really need to worry about that, right? Really, we just want to look at the shifts. So if we apply field again along the A-axis and measure the PL, again, we start with some energy, and as we increase the field through the Canting field, that shifts to some value once we're in the FM state, right? This is just like what we've seen before. However, if we then increase strain to about 1.7% or larger, we measure the exciton at the FM energy, and it never shifts with field. So what this is telling us is that through strain, we can induce an antiferromagnetic to ferromagnetic transition. And then once we apply field, we're rotating the spins, but their angle never changes. And so that exciton shift never changes. So this is a really powerful idea, right? We can now use strain and no induced magnetic field to change the magnetic ground state of the system. Okay, and then this down here is just how we calibrate the strain through Raman shifts. Okay, so with that, that's all of the sort of background. I'm going to get into the new work. This is a paper that we took some data for that was published in Nature earlier this month. I will have a sort of DOI for it at the end of the talk if anybody is interested. And what I have here is just a GIF playing that I'm going to let play while I'm explaining the rest of the slide. That's showing pump probe data. This is transient reflectivity. We have the time in picoseconds along this axis. This is field in the out of plane direction, so along the C-axis. And then we have the Fourier transform of that on the right. And these two panels are just showing a slice, where this dashed line is sort of rolling through the data. And so what you'll see is we have no signal at first, then we start to see this strong oscillatory signal that sort of softens with field until we measure, until our signal sort of goes away again once we reach the FM state. So what is happening here? What we have in our system is an ultra-fast pump that is way above the band gap. So we're injecting lots of hot electrons into the system. And within a few hundred femtoseconds, maybe under a picosecond, these carriers are going to thermalize down to the band edge and reach some thermal equilibrium. As they do that, they are ejecting lots of energy carriers, mostly phonons. They may be directly ejecting some magnons, we're not sure yet, but we are pretty sure, and the details are in this paper, that we are ejecting phonons, which then eject magnons or emit magnons. And so as the system cools down, we are putting a bunch of magnons into the system. This is an incoherent process, but the magnon precession is so slow that the 500 femtoseconds or so that this takes is viewed as essentially an impulsive perturbation of the system. And so the magnon precession is coherent. The phase difference over that 500 femtoseconds in the magnon precession is just so small that it doesn't decohere the system. And so what then happens is as the system, as the magnons precess, there are modes for which the angle between spins and adjacent layers is changing, right? So we can look at this picture, and this is not exactly what our system looks like, but if we view this as one layer of the crystal and another layer of the crystal, it's pretty close. Just sort of turn it on its side. However, it's an AFM, so we know there are two magnon modes, right? There's an in-phase mode and an out-of-phase mode. The in-phase mode is going to look something like this, where each of these arrows, again, is sort of one of the macro spins for a layer. And in the in-phase mode, they're just going to sort of wobble like that, but their angle never changes. And so the exciton shift never changes. That's what this plot is showing. However, they're in the out-of-phase mode, they do something more like this. If you can see my fingers, it's sort of the best way I have to draw it. And their angle is constantly changing through the Magnon precession. We can see that reflected in an exciton shift. Now, the way that we measure our signal in a transient reflectivity experiment is by overlapping the laser with the exciton. And our laser has a finite bandwidth. So as this exciton is shifting along with the Magnon precession, it's essentially changing the amount of overlap that our laser has with the exciton resonance, which then gets written as an amplitude modulation onto our signal. And so we can take that and use that as essentially as a proxy for the spin wave. And so this really is exactly that question that I mentioned before. Can we optically address these magnons? The answer actually turns out to be yes, right? So we can generate them with an ultra-fast pump pulse. We can measure them with an ultra-fast probe pulse without any external microwave system or contacts or leads or anything like this. All of this data is taken on a bare flake on a silicon substrate. Okay, great. So that's sort of how we measured the Exciton-Magnon coupling in the system. And there's quite a bit more in this paper. I encourage everybody to read it, but I'm going to move on to the other results now. And that is what happens when we start applying an in-plane field instead of an out-of-plane field. And so what we did is we took similar crystals. These again are just exfoliated, thin bulk, maybe 10 nanometers thick crystals on silicon dioxide. And we measure the same, we essentially do the same experiment, but now with the magnetic field applied along the A-axis of the crystal. So this is the intermediate axis. It turns out you can also measure along the easy axis, but the response is not particularly interesting. There's no magnons that you really see, and you just see a sort of step function in your response when the saturating field happens. So if we then go along the A-axis, this intermediate axis, what happens is the spin configuration starts to look like this, where again, we're canting, but now in plane. And if we measure the field dependence of the magnons, it looks pretty similar to what I had in the last slide. We see this mode that sort of looks like what you would expect from Landau-Lifshitz-Gilbert equation. We know that there should be another mode. These are the acoustic and optical magnon branches, but I'm actually going to call them dark and bright, this sort of D in a ket and B in a ket. That's not optical selection rules, dark and bright. That's just whether or not we are sensitive to them, right? So this is the mode that doesn't couple to the exciton. This is the mode that does. Their precessions look something like this. And again, this is what I showed you in the last image, just how that correlates to that exciton resonance energy. Okay, so if we take some line cuts out of the data at selected magnetic fields, we can see, yeah, this is just a single mode. It's got an exponential decay on it. The oscillations are really beautiful in the data, but it's not anything that's that exciting or interesting compared to what I showed you here, right? And so we wondered what else we could do with this system and took a little inspiration from some predictions and also some experiments that were done on chromium trichloride, which is another layered antiferromagnetic van der Waals material. This one, however, is an insulator. So what we have here is just some theory work done showing how you can get hybridization between magnon modes and self-hybridization between the same magnon mode in the CL3 crystal, showing that it's essentially possible. And then this work down here is some experimental work from a few years prior, actually. This is from a group at MIT, showing, again, you have this sort of acoustic and optical magnon modes, and they're applying an out-of-plane field, but as they rotate that field towards the sample plane, you can break symmetry in the crystal and start to induce some hybridization between these modes. So this is a completely different experimental setup to ours. This is microwave absorption measurements, kind of what I showed you on that first slide with the contacts and running AC currents through essentially a microwave waveguide. But the result is pretty exciting. And so we wanted to know if we could do something similar. Okay, and so the answer is yes. As you can see, as we start applying our field off axis, this is about 2 degrees in plane. from the a-axis. It looks something like this in a cartoony version, right? So intermediate axis, easy axis, and then our field is applied at some angle theta AB. We see a really distinct avoided crossing in the spectrum, right? So we have the same dispersion that we had in our bright mode before. We can see our dark mode now because of the sort of tails coming off of the avoided crossing, and then at a certain point we have that avoided crossing. This is in the time domain. We can also see that, right? We have mono exponential decays on top of a single frequency sine wave. If we measure at low fields or at high fields, but right at that central field, you see a beating pattern that has nearly unity modulation depth, meaning that essentially we have equal portions of both modes. At this point, right at the center of the avoided crossing, our mode will look something like this, where essentially one of your layers, the spins are locked, and in the other layer, they're processing with twice the amplitude that they were, in the unhybridized case. And then the exciton modulations will look something like this. This is just a sort of cartoony picture, but you can see that there's some character of both modes in the precessions. And so you essentially have sum and difference frequencies as a shift for each of these hybridized modes. Okay, and so this is pretty exciting, right? From this quantum information or quantum transduction standpoint, we take the idea of, okay, we can optically address these magnons to now, oh, we can optically address these magnons and we can generate a two-particle system, right? That's pretty exciting. So how can we control that, right? It turns out, just like in McNeil's paper from a few years ago, where they were, again, taking an out-of-plane field and turning it towards the plane, we can do something similar. So we can take the angle theta AB, which I, again, defined here, and we can increase it. So here we have 3 degrees, 6 degrees, and 9 degrees. And this top row is data. The bottom row is simulations that are just based on sort of a macro spin model. Again, the details will all be in the paper, which I will have a link for at the end of the talk. And you can see they match really, really beautifully, which is pretty exciting. But what we have is, as we increase the angle of the field, we can see a few things happening, right? So first thing, the splitting at the avoided crossing is getting larger. And if we measure that splitting from the data, we can see that it's roughly linear over the range that we were able to access in our experiment. So the theory tells us that this will eventually saturate, and depending on what field strength we're at will look slightly different. But in the small angle limit, it will be roughly linear. The strength of the field will only change that angle, essentially, the slope of this line. The other thing that we can do is we can get an idea of how strongly the dark mode now couples to the exciton, right? And this is kind of important because the Magnon-Exciton coupling is really what defines the Magnon light coupling, because the exciton strongly couples to resonant light. And so anything that couples to that exciton, we can also optically address. And so this is one of the kind of important things that we wanted to figure out in this study was, can we control the amount of light that accesses this dark Magnon mode? And again, it turns out the answer is yes. So you can see as we increase the field angle, these tails that sort of fly away from the avoided crossing get longer and longer and brighter and brighter. And again, if we measure that, we can essentially measure this peak at 0.3 Tesla or something like that, something away from the avoided crossing, and again, see that it's linear with increasing angle, for points that are above the noise floor. This is below the noise floor, for example. In the time domain, we can see if we measure at the avoided crossing in the time domain, we can just see that beating pattern getting faster and faster, which is what we expect. And then finally, as a last note, because this is going to be on the next slide as well, these white dashed lines are what the unhybridized modes would look like. So that'll become important on the next slide. And so again, if I return to that original question, or that original prompt of what we really want out of this system, is we want an optically addressable system for sort of quantum information ideas. This now gives us the ability to tune a lot of these parameters, right? So we can generate, we can use laser light to generate a two-particle system. We can make those two particles interact. We can control their interaction strength, and we can control their relative amplitudes through some amount of tuning the angle of the field and the strength of the field. So this is really exciting stuff, as far as I'm concerned, right? This affords us a really powerful amount of control over what we would see were we to use this as a quantum information platform and how we could control it. So really, though, we weren't quite satisfied with that. What we wanted to know was if we could further control this. Specifically, we wanted to know if we could control the curvature of these Magnon bands with respect to magnetic field. The idea here being that, if we can tune the behavior of the magnon with respect to field, then we can set it in a configuration that allows us to tune the field and get the behavior that we want along with the angle, right? So again, we're just looking for ways to control how these things behave. And as I mentioned to you before, we know that strain can act as a really powerful tuning knob, especially in this system. This is where I showed you the AFM to FM transition can be induced just by strain. And so we decided to apply the same idea here. So if you remember that strain application or apparatus from before, which had those piezos, that's what our sample is going to be sitting on. What we have is a slightly different way of doing it now, where we take a thin layer of polyamide, which is a flexible, transparent polymer. We lay our CrSBr crystal on top of that, and then we evaporate gold on top of that. We leave a small window for optical access, but the gold is essentially acting as a clamp to keep the CrSBr from slipping as we apply tension to the polyamide. We get better strain transmission this way, and we can get upwards of 2% strain. We didn't quite get that on this exact sample, but 1.5 to 2% is roughly the kind of strain application that we can get to the crystal itself. Okay, so now if we take a look at the data, this is set up similarly to the last slide where we have data on top and we have simulations on the bottom. The data quality is a little lower. That's just an artifact of the substrate choice. It just gives us less reflected light. But I think you can still see the trends pretty clearly here and how well they match with the theory. So what we have on the left is a low strain case. It's 0.48% strain, which is relatively high in the grand scheme of things, but we're going to go much higher. So we're going to count this as the low strain case, all the way up to about 1.3. We have data that goes much, much higher than this. But at a certain point, you reach the ferromagnetic state, and we are not sensitive to magnons in the ferromagnetic state. And so the data just becomes kind of nothing. So as we look through this, this increasing strain, we see two things, maybe more, but let's start with two. The first thing we see is a decrease in the saturating field, right? This is where we switch from AFM to FM. And you can see this really clearly because it's where our magnons stop being present, right? The idea here is that in the ferromagnetic state, the angle between spins is always locked. So no matter what magnon precession is happening, we're not sensitive to it because it doesn't affect the exciton resonance energy. So you can see that here we can't quite reach it. It's a little bit past the roughly 0.85 limit of our in-plane field. You can see it come down a little bit as we increase the strain, a little bit more and a little bit more. So that's consistent with this sort of idea of a strain-induced transition from AFM to FM. The other thing that we see is a change in the shape of these magnon bands, right? So you can see a pretty significant change in the curvature of the magnons between the low strain case and the high strain case, right? And I'm going to return to that in a second. But first, I just want to mention that this is actually a really nice way to pull out some magnetic parameters that are actually really hard to measure in these AFM van der Waals systems. So that's what I have up here in these top two plots. This J2 is the interlayer exchange energy. This is essentially going to tell us whether neighboring layers are AFM or FM coupled, right? So once this crosses 0, our crystal would become ferromagnetic. And this KB minus KA is essentially the difference in in-plane magnetic anisotropy energies. Any changes in this would indicate a change to the EZ axis of the crystal, for example. Excuse me. And so what you can see is that as we increase strain, this difference in anisotropy energies is pretty much constant to within some noise fluctuations, indicating that the orientation of our magnetic axes is not changing as we strain the crystal. However, we do see a huge change in the interlayer exchange energy. And so what this indicates to us is that that strain-induced transition from AFM to FM is really driven by changes in the interlayer coupling. So as we strain the crystal, we're changing the interlayer coupling such that it favors FM at high strains. So this is a really interesting thing that was sort of a side effect of this measurement that we did that we didn't expect, but could be quite useful for measuring these sorts of properties in other materials. So if we go back to sort of the Magnon data here, one thing that I want to point out to you, and this is something that we really don't have an explanation for yet, is that there is a critical strain. Here it's about 1.18%, where we have a Magnon with no field dependence. So, you can see at low strains, our dark Magnon and our bright Magnon have opposite curvatures. At high strain, you can see they have like curvatures. And so, we knew this was going to happen, but we did actually find it. And, this is what we get from the theory, but it matches well enough to the data that I believe it. And we're not sure what this means yet, or what possible properties it has, but it is an interesting curiosity. And I thought that the people who attend talks like these would probably be quite interested to see it. So if anybody has any thoughts or ideas, I would love to talk about it, because it's something we want to measure more. We just aren't sure, what sort of things we should be thinking about for this sort of Magnon state. Okay, so that's all the data I have to show you. I'm going to take us back to that initial slide to sort of think about the context of this data and how it sort of relates to what I talked about earlier. So if we think about Magnons for quantum transduction, what we've shown in this system is that we can now bypass a lot of the difficulty in sample fabrication that used to be necessary, right? So we have a system where we don't need to do any sort of device fabrication to generate Magnons. We can do that with an ultra-fast laser pulse. We also don't need any specific geometry, optical fibers, anything like that to measure the Magnons. We can also do that optically, just all based through this sort of excitonic proxy measurement, which means that we can take this system, we can couple it to a superconducting qubit, and then directly optically access the Magnon, communicate with the superconducting qubit, even though these differ by orders of magnitude in the energy. So I think this is a really, really exciting prospect on its own. But then if we start to think about this Magnon information, what I hope I've convinced you of is that CrSBr is a system where we can now use these ultra-fast laser pulses to generate a variety of two-particle states. We can control them to a high degree, to a degree that I don't know we've seen before. And given how well the theory matches, that we can predict exactly what the system is going to do and reproduce that in data, all of which I think are extremely important for these kinds of applications. So I have changed our optical question mark to optical exclamation point. I hope that you guys are as excited about this system as I am. And we are sort of working feverishly on ways that we can sort of exploit what we're seeing and further it. And so with that, I do just want to give out a couple thank yous and do some sort of wrapping up. Obviously, I want to thank Shin and Carol for letting me talk and for organizing this seminar. I've been attending for the last 6 weeks or so, and they've been incredibly helpful for my understanding, not originally coming from a Spintronics background. I also want to thank everybody else who helped with the work, Eunice, Daniel, Xiaoyang, and Xavier, as well as John, Yafi, Jordan, I forgot to list, but him, Dee, Ting, Xiaodong, and the entire Shu group. Finally, funding sources, the US Department of Energy and my fellowship agency, intelligence community, postdoctoral research fellowship. If anybody is a postdoc or has a postdoc who is a US citizen and wants some funding, I would be happy to give you some information. It's a very good opportunity that comes with lab funds, travel budget, and it is a really great opportunity. Finally, the papers can be found here for the Exciton-Magnon coupling and here for the Magnon-Magnon coupling, and you can visit our group webpage as well. And this is just a picture of our group. So thank everybody for listening. I'm happy to take questions now.
Thank you very much for this interesting talk. First, we can thank the speaker by using the reactions buttons. Now, this talk is open for questions. If you have any question, please raise your hand in Zoom. And if you're watching this on Twitch, just type your questions in the chat box and I can read it for you. Okay, do I have any questions in Zoom? Let me start with the very first question. I want to understand a little bit more details about the optical excitation of the magnons. Now, I understand that when you do the photoluminescence experiment, you find that when it turns from the ferromagnetic to antiferromagnetic state, the resonance energy is has a quite significant shift. And then, therefore, if there's any magnetization precession, that will also cause the shift of the energy. Yeah. So that may be the reason of why it would significantly couple to the exciton. But when you actually do the experiment to do the measurement, you use an ultrafast laser pulse to excite that. And how to detect that? Was the detection of the photoluminescence, or was it like a curve microscope?
Yeah, so I didn't want to get too into the details because I know this is not an optics seminar and I can get pretty heavy into that. But what we're doing is transient reflectivity. So what we're doing is we send in a pump pulse, and then with time resolution, all we do is measure the amount of light we get reflected back from a probe pulse. We put our probe pulse, so if this is our exciton, we put our probe pulse right on top of it. And then what happens is as the magnon precesses, the exciton shifts into and out of the laser spectrum, which then changes how much gets reflected back. And so if I go back to some of the data, essentially the spin wave gets written as intensity modulation on our reflectivity data. And so we don't need anything, any special microscopes, any magnetic spectroscopy. In fact, we've even done some magneto-optical spectroscopy, and the data looks essentially identical. Yeah, so the detection is just based on, and what I will say is if you use a broadband pulse, for example, you actually don't see these, right? Because the shift of the exciton stays within the laser bandwidth. So it's pretty important here that we use a finite laser bandwidth. But yeah, really we're just seeing the exciton shifting in and out of that spectrum.
I see. Thank you very much for the explanation. Professor Jaswal, please go ahead.
Oh, your electron phonon coupling are playing the role when you apply the strain, I believe. So are you able to get information about the electron phonon coupling from the data?
Yeah, so we've tried a little bit. The biggest setback for us is the time resolution that you need to measure. So the phonons are in the terahertz range, right? And the time resolution that you need is much higher and requires much longer data acquisitions if we want to get the entire Magnon precession. And so we have not done that, but this Nature paper has looked into some Magnon transport and how that is affected by essentially the anisotropy of the crystal, and link that to some of the phonon behavior. This is how we know that some of this electron phonon coupling is what's mediating the Magnon generation. And so we have some idea. I wouldn't say we know. We haven't measured any phonons or anything like that, but we do know that they're involved in the Magnon generation process. I think getting a better measure of how that magnetostriction happens is something I would like to pursue further. But I don't have any quantitative answer for you there.
What are the excitons? I mean, how do you? Physically, what are the excitons that you're talking about in the system?
In energy?
No, I mean, what is this localized or whatever? Is this you talking about magnetic exciton?
Oh, I'm sorry. No. This is an electron-hole pair that's excited when we excite the crystal with light.
Yeah, so you also have when those bands separating Magnon-Magnon interactions.
Yes.
Are you able to separate the Magnon-Magnon from electron-phonon in terms of the separation?
So they should happen at very different frequencies. In fact, my guess is that the frequency of like electron-phonon coupling is going to be orders of magnitude larger than this. And so I don't even think that the measurement that we have is sensitive to the electron-phonon interactions. I just think it's happening too fast for us to measure.
Okay, thank you.
Yeah.
Great. Do we have any other question from the audience? I want to ask a follow-up question. When you do the excitation, do you see any chirality selectivity? Like if you use the exciter with a left-handed or right-handed circular polarized light?
Yeah, so it's a good question. We actually haven't tried doing any circular polarization dependence in these measurements, mainly because the exciton itself is extremely linearly polarized. And so my guess, though we haven't tested it, is that you won't see any difference because the exciton won't absorb, so you can think of your circular polarized light as a superposition of two linear states. The one linear state is just not going to be absorbed into the system at all. So that's for the exciton states. For just free carriers in this above band excitation, we know that that's not polarization sensitive in the same way. And so we could try doing some excitation, some circular excitation there. Where it starts to get a little trickier is that when you circularly polarize an ultra-fast laser pulse, it does carry a pretty significant magnetic field. So it will apply an induced magnetic field to the system in the Z direction. And so that would just be an extra thing we would need to unravel from this whole system. And so we haven't tried it yet. But I think it is, there's always a long laundry list of things to try, and I think that's on there.
Of course, yeah. Thank you.
Mhm.
Kirill, please go ahead.
Yes, thank you. I have, I think, a simple question.
Okay.
So if I understand correctly, the dark mode is an acoustic magnon.
Yes.
And the bright one is an optical magnon where the different layers oscillate out of phase.
Yes.
So I'd like to understand why those modes cross in the magnetic field. Is there a simple explanation for that?
Yeah, so there is, it has to do, so you're getting slightly out of my understanding because we're starting to enter into my colleague Geoffrey's realm of theory. If I recall right, there is it just has to do with the symmetry of the crystal, causes a gap in the acoustic mode at zero field, for example, and causes the curvature of it to bend the way that it does. I think this is also, the same reason why sort of using these symmetry breaking fields allows for the hybridization of the modes, is I think that these are all sort of symmetry effects from the crystal and the magnetic anisotropy. This is, again, what I recall from what he's told me, but I can send you, I think I sent you guys the paper, but there's a description of the theory used to model the system in the supplementary information. And we could take a look at that and see if that's explained.
In that archive paper?
Yes, I can't remember if the supplementary information is included there. If it's not, I'm happy to send it to you.
Okay. Thank you.
All right, great. Do I have any other question? Let me just quickly check Twitch. Okay. Looks like we don't have any immediate question for now. We have another session right after this for further discussion, but at this moment, I just want to thank the speaker again. And
Very nice talk. Very nice talk. Thank you.
Thank you. Thank you for having me.